Experimental procedure. 1. Use a tape measure to measure the height h between the base and the floor. Be careful, the height h must be in meters. The students should measure in centimeters first, then convert it to meters. It is recommended that they use 3 significant figures. For example, if h equals 129 centimeters, it equals 1.29 meters, etc. 2. Turn the wheel so the rope wraps around the shaft until the saucer is leveled with the base. Then, add a mass of 20 grams to the saucer. Therefore, our first experiment will record a mass m of 20 grams plus the mass of the saucer m0, for example. If the mass of the saucer is m0 equals 27 grams, then the mass m for the first experiment is equal to 20 gram plus 27 gram equals 47 gram, etc. 3. Release the saucer with the weight and measure the time it takes to hit the ground. Repeat this process at least 3 times and find the average time. Four. Repeat step 1 by adding more mass to the saucer 3 more times, increasing the mass by 20 grams each time. Five. Calculate the linear acceleration for each mass m used in the motion. Then, calculate the torque of the inertia wheel set and angular acceleration alpha, where acceleration a is calculated from the equation a equals 2h divided by t average squared. The results are determined using the multiplication principle involving significant figures, which will follow the rule of the least significant figure. For example, a equals 2 times 1.29 divided by 123.6 is equal to 0.0208737 meters per second squared. The number 2 has an infinite number of significant figures. 1.29 has 3 significant figures. 123.6 has 4 significant figures. The least significant figure is 3, so a equals 0.0209 meters per second squared, etc. Torque is calculated using the equation torque equals m times g minus a multiplied by rh, where the acceleration due to Earth's gravity is g equals 9.782 meters per second squared. The term g minus a is calculated based on the significant figures rule of addition and subtraction. The answer should have the same precision as the least precise value, resulting in 3 decimal places or 4 significant figures. When this result is multiplied by the mass m and the radius of the shaft rh, the final answer follows the multiplication principle. Division involving significant figures, the answer should have the same precision as the least precise value. For example, torque equals 0.047 times 9.782 minus 0.0209 times 0.0390, which equals 0.01789 Newton meters. 0.047 has 2 significant figures. G minus a has 4 significant figures. And 0.0390 has 3 significant figures. Therefore, the least number of significant figures is 2. Thus, the torque is equal to 0.018 Newton meters. The angular acceleration, alpha, is calculated from the equation alpha equals linear acceleration, a, divided by the radius of the shaft, rh. Therefore, the results are determined according to significant figures multiplication and division rules. The answer must be rounded to the least number of significant figures in the given data. For example, alpha equals 0.0209 divided by 0.0390. which equals 0.535897 radians per second squared. 0.0209 has 3 significant figures, and 0.0390 has 3 significant figures. The least number of significant figures is 3. Therefore, the angular acceleration, alpha, is equal to 0.536 radians per second squared. 6. Plot a graph of torque versus angular acceleration, alpha, with torque on the y-axis and alpha on the x-axis, as shown in the example picture. Then, draw a straight line that best fits the points obtained from the experiment. 7. Find the slope of the graph and use it to determine the moment of inertia. The relationship between torque and angular acceleration, alpha, is given by torque equals I alpha. Therefore, the slope of the graph between torque and alpha represents the moment of inertia of the system. Thus, the slope, g, equals the moment of inertia, I. By rearranging the equation, we get the moment of inertia, I, equal to the slope, g. This moment of inertia value is obtained from the experiment. Since the slope's units are determined by dividing the y-axis units by the x-axis units, the moment of inertia obtained from the graph will have units of Newton meters times seconds squared per radian. However, since radians are not considered units in the SI system, they cancel out. Therefore, the moment of inertia obtained from the graph will have units of Newton meters times seconds squared. We will use the experimentally obtained moment of inertia to compare it with the theoretically calculated moment of inertia. 8. Calculate the moment of inertia from theoretical calculations and compare the values obtained from the experiment to find the percentage error. Since the wheel and shaft system are cylindrical and rotate around the axis of the cylinder, with the axis of rotation passing through the center of mass of the cylinder, the theoretical moment of inertia of the wheel and axle is given by I equals 1/2 mdrd squared plus 1/2 mhrh squared, where md and rd are the mass and radius of the wheel, and mh and rh are the mass and radius of the axle. The unit of the theoretical moment of inertia is kilogram meter squared.